All right. So we're going to be dealing with the functions f and first derivatives with our calculator and kind of analyzing using our calculator, helping us figuring out what's happening with the original or what's happening with the derivative. So the function f prime of x equals cosine ln of x is the first derivative of a twice differentiable function f of x. So part A, on the interval from 0 to 10, find the x values where f of x has a relative max and justify your answer. Alright, so the first things first. If we have a derivative, how do we find critical points of that? Set it equal to 0. So if we set our derivative equal to 0, is this an easy one to solve? Not really. Well, luckily we have a calculator. So go ahead and pull out your calculator. Go to the y equals key. And on mine, you're going to see a lot typed in here because I've been using it for different things. Do you guys know about highlighting the equal sign? It will only graph one of them at a time. Do you guys know about that? So if you have more than one function listed in here, do you see how this equal sign on the y1 is like blacked out there? That one is going to graph. So if I would go down to this one and go over and hit enter, it would make that one black, so it would graph both of those at the same time. But I'm only worrying about my cosine of ln x right now because that's the only one I'm messing with, so you guys can ignore those right now and just type in the cosine ln of x. So don't worry about anything else I have typed in there. But just knowing on mine, the only one that's going to graph will be the top one. That's the only one I have highlighted. So when you actually graph the cosine of ln of x, you're going to get this graph here. Now we need to change the window a little bit. Mine's already adapted a little bit, so your window, I have mine, x's, I started at -2, even though we're dealing with these values here, from 0 to 10. So I started a little bit before 0, and I have it end at 10, so I went from -2 to 10 on my x values. And on my y's, I went from -2 to 4. That way it's easier to view close to the x-axis. -2 to 10 and -2 to 4. Okay. And you don't have to do exactly that, but close to that. But especially you want to go up to 10 because we're dealing with x values from 0 to 10. So when you graph it, does everybody get something similar to this? Okay, so at this point we're still trying to figure out what our critical points are. And again, we mentioned the critical points are where it's equal to 0. By just looking at the graph, do we see anywhere where it could possibly be equal to 0? Daniel?
Somewhere around 5.
Okay, so somewhere out here it looks like it's equal to 0. Does it look like it could be equal to 0 anywhere else? Dan?
Right next to the y-axis.
Yeah, if you look really close, it looks like it's crossing and actually going below that. So if we have a graphing calculator, how can we actually find out what those points are? Go ahead.
You could have it find the roots.
Okay, do we know how to calculate that or find that on the calculator? If we go to, it would be second, trace, which is the calculate button. We want to actually find what out of that list? Yeah, we want to find a 0. We're looking for when the critical point's there when it's equal to 0, so we're trying to find a 0. So go down to 2, we're trying to find a 0. It's asking for a left bound. Okay? Well, we'll start with this one because we know for sure this one crosses over here. So go on the left side, hit enter, somewhere on the left side. Scroll over and get somewhere on the right side. And then hit enter twice and you will get your answer. It should show you y equal to 0, and that'll show you where we're at on the x-axis. So in terms of this problem, when cosine ln of x is equal to 0, one of our x values is 4.81. And we used the calculator to help us find that. But we said, I think Daniel mentioned that it looks like there's one really close to the y-axis here. So let's go to second, calculate again. We want to find another 0. And we need a left bound, so we got to go way over here. And there, it looks like I'm way to the left now. I'm way down here on the bottom of the screen flashing. So I'm going to hit enter there. Scroll back up, find somewhere on the right side. And it does give me a y equals 0. So this is a 0 here, and I get an x value. Is anybody not able to get that or need help with the calculator? I can come around and show you. We're okay? We all found that? Alright, so we found our zeros. So now that we're dealing with our zeros here, those are critical points. What do we normally make once we have our critical points? Yeah, we make that chart. So we're going to deal with some intervals here. Where is my first interval starting? Yeah, so don't be tripped up here. A lot of the ones we've been doing have gone from negative infinity. Remember, the problem said from 0 to 10. So the first number we can have is 0. And where are we going to stop first? 0.208 or 0.21, depending on how you rounded. Yep, our one critical point. And then we're going to have the 0.208, and it's going to go into our next critical point, 4.81. Okay. Then we're going to go from 4.81 till where? 10. Yeah, that's the end of our interval. We can't go any further than 10. Very good. We're going to create our table. Alright, so f prime of x. We need to find whether it's positive or negative within these values here. So again, you have a calculator that could help you. You have the graph of f prime of x. If you're anywhere from 0 to 0.208, if you don't want to plug something in, look at your graph. If you're from 0 to 0.208, that's where it touches the x-axis, are you positive or negative? You're negative. Then look from 0.208 until you get to 4.81. So all the values in between here, are you positive or negative? Positive. And lastly, from 4.81 until you get to 10, you're what? Positive or negative? Negative, thanks. All right. So far, the question said, on the interval from 0 to 10, find the x values where f of x has a relative maximum. Justify your answer. So we started out with the derivative, found our critical points, we created our table, and now we need to answer the question. What x values does f of x have a relative max? And justify your answer. How do you know that? How do we know that the original has a max? Braden?
If f prime of x changes positive to negative.
Yeah, from positive to negative. So right here is a max. What's over here? A min. They don't ask about the min, but we can label it. So we would have a min at this point. We have a max at this point. So justify your answer. Well, we're going to say f of x has a max at x equals 4.81 because f prime of x does what? We just mentioned it, but
Changes positive.
yep, exactly, because f prime of x changes positive to negative. Changes positive to negative. Do we have any questions on how we found that max? With the calculator, we're okay with how we found the zeros? All right, so if there's no questions with part A, let's go to part B. So it's going to be dealing with the same function because we're underneath this still. So part B, on the interval from 0 to 10, well, nothing has changed. We're still dealing with the same function. We're still dealing with the same interval. Find the x values where f of x has a relative min. Justify your answer. Well, have we already done the work for this? Yeah, we have. So we know f of x has a min at x equals what value? Yeah, 0.21 or 0.208, however you rounded. Because f prime of x changes what? Negative to positive. You stole that one from Stevie that time. And that's all they're asking for part B. So we did all the work in part A. That was all the hard work. We used the calculator, found the table, but it helped us with problem B. We didn't have to do any extra work. We just had to look at our table. All right, let's go into part C. On the interval from 0 to 10, so we're still in the same interval, find the x values where f of x has a point of inflection. Justify your answer. All right. So point of inflection. So we need to think of this. How can we use the first derivative? And remember, we have the graph of it if we need to use that. How can we use the graph to determine where we have a point of inflection in the original? If you think about having the original, if you have an inflection point, you take a derivative, what does it look like on the derivative? So take a minute. If you need to talk to somebody around you, try to brainstorm. If you have the original, you take the derivative of it at that inflection point. What does the derivative look like at that point? What's actually happening? Any ideas? Hear a little bit of talking going on? Daniel?
We're looking for where we think the point of inflection is correct.
So we want to know on the original where the point of inflection is. So how can we use the first derivative to help us find that on the
By
original?
using the maximum, because that is a point of inflection.
Yeah, we can use the max or min from a derivative, and that will tell us where the inflection point is on the original. From 0 to 10, do we see somewhere where we may have a max or a min?
Yes.
Yes, we do. So if you want to draw that on your paper, so if you look back in your notes and you don't have your calculator, you know what we're talking about. It's going to go up like this and down, something like that. And we know we have, well, we don't know what it is yet, some max value here. Okay? This is f prime of x. So, if you have a calculator, can't you find a max on your graph? Go to second, calculate, down to 4. That's where maximum is. Again, just like we did with the zeros, get a left bound, get a right bound. And what is your 0? Or not 0, your max, sorry. Anybody not able to get it? Daniel, what'd you get?
My answer looks different from yours. I got 1.
Yeah, that's what I have. That's gonna run. It's 1.00000. So yes, 1. So we know that it's gonna be at x equals 1. That's where our max is. So f of x has a point of inflection, POI, point of inflection, at x equals 1. You can say 1.000 it went on, but 1. Because f prime of x has a max. Which means f double prime of x does what? So we know the original had a point of inflection at 1. We see the derivative graph right here. We know it has a max. So what's happening if we have the second derivative? So we take the derivative of this derivative. Daniel?
F prime of x will be changing from a negative to a positive, but from a positive to a negative.
Correct. The second derivative is. So if you take the derivative of this, we're going from a positive to a negative. So f double prime of x changes sign. And if you think back with those second derivatives that we were dealing with in our charts, if you have a second derivative chart and you show a change of sign, what does that tell you about the original? We just described it here, but what does that tell you about the original? You have an inflection point, yes. But if you have the first derivative, you're looking for that max or min. From 0 to 10, do we see any other maxes or mins that could be potential inflection points? No, that's the only possible max we can see. All right, very good. So that's all for this first problem. Do we have any questions about this problem in particular? All right, if there's no questions about this problem, let's go down to the next one. So this one's actually like a multiple choice question, but it's still we can use the calculator to help us out. So on this problem, on the interval from 0 to 10, how many relative, and we want this to say, I believe this should say maximums here, but we'll start the problem and then we'll see what it does. So from 0 to 10, how many relative, it says mins, does the graph of g of x have if g prime of x has sine x over x plus 2? So I already have this typed in my calculator, like I said earlier, but you can delete what's in there and put it in your number 1. But you need to have sine of x divided by x plus 2. So you can delete what you have in the first one and just put this in your first one. But sine of x divided by x plus 2. With this problem, when you graph it, we're dealing with the interval 0 to 10 again with this problem, so you could leave from negative 2 to 10, but we may have to change our x and our y's. Let's see. Maybe not. So it seems like it's zoomed out a little far. You get something similar to that if you kept the same bounds? Let's try zooming in a little bit. So we'll go to Window. We want to change our y values. So maybe negative 1 to 1. Let's see what that looks like. All right. So again, let's change this to relative maxes. So if you're analyzing this graph, you have it on your calculator. We're going from the interval. Now remember, we need to ignore this over here because we're starting at 0. We're going from 0 to 10. We want to know how many relative maxes would the original g of x have. Remember, this is a derivative graph. We want to go back to the original. So how many maxes are on the original? I'm going to draw the graph here on my paper too. Okay. So what are we looking for? Remember, this is g prime of x. This is the derivative. On the original, though, we want to know if it has where the relative maxes are. So how do we find that on the original? Daniel?
Whenever the derivative function crosses the x-axis, you can identify if it's a max or min, if it goes from positive to negative or negative to positive.
Correct. So in this case, we're looking for what? Because we're talking about maxes.
Positive to negative.
Okay, so we're looking for positive to negative. So how many do you see on your graph?
2.
All right, we go from positive to negative right here. We go from positive to negative right here. There are 2 spots where you can have a max. That's what the question's asking. All right, if we're okay with that, we'll go to the last page. All right. The derivative g prime of a function g is continuous and has exactly 2 zeros. Where are those zeros at on the chart? Which x values?
-2 and 2.
Okay, those are the exactly 2 zeros they were talking about. Selected values of g prime are given in the table. So we have x values, and these are g prime of x values. If the domain of g is set of all real numbers, then g is decreasing on which of the following intervals? So again, this is the derivative up here. We want to know from the derivative values given, where do we know that the original is decreasing? And think about that. If the original is decreasing, what must the derivative be doing? Or what must the derivative be? Negative. So we know g prime of x has to be negative if g is decreasing. So if you're reading through a problem, maybe write yourself some notes when you're trying a problem like this. It may help you out. So we know g, the original, is decreasing. If I take the derivative of something that's decreasing, I know the derivative will be negative. So now go back to your table. Where's the derivative negative? From where to where? Because we're talking about an interval. Steve? From -2 to 2. Is -2 and 2 included? No, because it's 0 there. It's not negative at that point. So, right here. Letter A. We're okay with that? All right, next problem. The second derivative of the function f is given by f double prime of x times x minus a times x minus b squared. The graph of the second derivative is shown to the right. For what values of x does the graph of f prime of x have a relative maximum? So we know we're given the graph of the second derivative. We know that. And we want to know about the first derivative having a relative max. We're given a picture of the graph. Now remember, again, if the second derivative and the first derivative are confusing you with relationship, think about it as the first derivative compared to the original, because it has the same relationship. So looking at that graph of the second derivative, where does the first derivative have a relative max? What are we looking for in the second derivative when f double prime of x does what? We could write ourselves a note, and then it will help us figure out looking at the graph. We're looking for a maximum, so if we take the derivative, what's happening at the derivative of a maximum? So think about that. If I have the graph of a maximum, and you're taking the derivative of it, going up, 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 and then the derivative is going to level out and go down, so what's actually happening? Daniel?
It needs to cross the x-axis.
Okay, it's crossing the x-axis, but it's what specifically if we're talking about a maximum?
Positive and negative.
Yeah, it's going from positive to negative. So now what we need to do is look at our graph and figure out where the second derivative is going from positive to negative. So, at what letter is it going from positive to negative? Any ideas? Somebody I haven't talked to today? We're looking where the second derivative goes from positive to negative. We have the graph there on the paper. Somebody I haven't talked to. Yeah, go ahead, Joseph.
Letter A.
Letter A. Is letter A the only one where it goes from positive to negative? I see some head nods. We all agree that's the only one? Yeah, over here we went from negative to positive, and over here we bounced off. We were positive, went to 0, and stayed positive. So A is the only option. That's the only place that the first derivative would have a relative max. Very good. All right, 2 problems left. If h of x is a twice differentiable function such that h of x is less than 0, this is going to be important later in the problem. So underline it or put a box around it. That's important. H of x is less than 0. Before we move on, if h of x is less than 0, what do we know about h of x? If it's less than 0, that tells us what? It's negative. Keep that in mind for later. That's true. That's negative. Okay, for all values of x, then at what value or values does the graph of g of x have a relative max? And we're given the derivative here. So we're given the derivative. We want to know a relative max of the original. So if we're finding the relative max of the original, what are we looking for in the derivative again? We've been talking about this quite a bit. We're looking where g prime of x does what? Think about the previous problem we worked on. Right now we're talking about the derivative and its original. We want the original to have a max, so what are we looking for in the derivative? Anybody have it? Use the previous problem to help you out. The derivative must be doing what? Somebody I haven't talked to today? Anybody have it? Anastasia, do you think you'd have it? What's going to happen? Exactly, yes. The first derivative has to go from positive to negative. So that's what we're looking for. Do we actually have a graph to plug into on this one? Or look at a graph? Do they give us one?
No.
No. Can we type this in and get a graph if we just have an h of x there? No. So
You could technically, because it doesn't matter what h of x is, as long as it's negative, it will just affect how the graph extends its stretch.
okay, we're saying the value of h of x is less than 0, true, but do we actually know what the function h of x is? Because this is saying the function right here. Whatever the function is, we would have to put that function here and type it in. But we don't actually know what the actual function is at this point. We don't know what h of x is equal to. Okay, so we can't just type that into the calculator. But we still may be able to find some critical points. Is h of x ever equal to 0? No. So we know it's never equal to 0. But can we possibly break down the derivative a little bit more? They gave this as the derivative, but can it be broken down a little bit more? See a couple head nods. Anybody figure it out? Dan?
3 minus x and 3 plus x.
I have 3 minus x and 3 plus x. So that is the 9 minus x squared split up, and we still have times h of x. Okay? So we really haven't done anything yet except simplify that a little bit. This is the derivative they gave us. But again, if we have a derivative, how do we find our critical points? Equal to 0. Well, we know this one is never equal to 0. But what if we set these two equal to 0? What do we get as critical points? Positive 3 and negative 3. Those are critical points. So again, now we can create a table because we have our critical points. In terms of this problem, where are we starting at with our first interval? Does it limit us at all? Does it tell us where we start? Does it blatantly come out and say we're limited from here to here? No. If you look at this, does it look like we could probably plug any value into this function at this point? Is there anything restricting us? Could we plug any number into here? Yeah, we could. So we're going to go from negative to positive infinity. So the first one starts at negative infinity and goes to negative 3. First critical point. Then from negative 3 to 3. And then from 3 to positive infinity. Okay. So we have our intervals. So now this is the part that could be a little tricky. So we need to figure out within each of these intervals if we're positive or negative. So we want to know if the derivative is positive or negative. So g prime of x. If we take a value in this interval, let's do this together. Somebody pick a value within this interval. Okay. We're going to go to the derivative. You can use the one we simplified or this one. So if you go to the original derivative, you plug in negative 4. What is negative 4 squared? 16. What's 9 minus 16? Okay, you get a negative. What is h of x? Well, we know from the beginning it's less than 0, so it has to be what? Negative. What's a negative times a negative? Positive. So we don't need to know what the actual value is, but we can still figure out the sign. That's why that first h of x less than 0 at the beginning was very important. We know that it's negative. They have to give that to you. All right, so let's do the same thing with the next one. What's an easy number in this interval to pick?
0.
Yeah, 0. So what's negative, or it's 0 at this point. 9 minus 0 is 9. 9 times a negative. Negative. Good. And go ahead and pick, you could pick any number between 3 and infinity, but maybe pick 4. You get 16. 9 minus 16, you get a negative. What's a negative times a negative? Positive. Okay, before we go any further, go back to the question again. What are they actually asking for? We wrote ourselves a note at the beginning, but what are we looking for? Yeah, we're looking for a max. So we're looking, remember we wrote ourselves a note, so we don't have to go back and figure it out again. We can look at our note that we wrote. G prime of x, we're looking for the derivative to go from positive to negative. Is there anywhere it goes from positive to negative? Yeah, right here. This is a max. At negative 3. So your answer is D. Again, it was important at the beginning to realize h of x, if it's less than 0, that means it's negative. So you can still plug into the derivative and figure out what the sign is. We don't know what the actual value is, but we know whether it's positive or negative. And then we're looking for the derivative to go from positive to negative. That gives us a max.
Why couldn't you have just... I did the problem a little differently. I understood that h of x needed to be a negative, and that even like the function of h of x is now irrelevant because it's negative. So I
Okay.
plugged in a negative one.
Just
for
a negative
simplicity
number?
and graphed it
Okay.
and got it. Like you could have put in a negative 100 and it went wow.
You could have, because h of x, whenever you calculate it, is going to give you
Has
some
to be
negative
negative.
number. True. You could pick some random negative number. That is true. And get an example on your calculator. Do you have that pulled up on your calculator?
Yes.
Can I see that first? Do you have, so it says that x equals negative
Yeah.
3. Does it show the max?
Yep. Which goes positive
Yes,
to negative,
all right.
negative to positive. Very simple.
So if you look at the calculator here, let's see. It's lit up a little different. Might be a little hard to see.
I can lower the brightness here.
All right, there it was.
Oh.
I think it was. All right, so he picked a random negative number to plug in for that h of x. What do you know what negative you plugged in?
Just negative 1.
So a negative number, because we know h of x is going to be negative. And he got a graph, and it goes through at x equals negative 3. And this is the derivative, remember? It's going from a positive to a negative, so we know there has to be a max in the original. So you could have done that too, correct. Very good. Are we okay with both ways of how we did that, using the table or the calculator? All right, one problem left. A table of function values for a twice differentiable function f of x is pictured to the right. Which of the following statements is or are true if f of x has only one zero on the interval from negative 3 to 3? So let's look at it one at a time. If the first derivative is less than 0, or is the first derivative less than 0 on the interval from negative 3 to 3? So think about that. They give you x values, they give you the function. We want to know if we would take the derivative, would the derivative be less than 0? One second. I'm asking, this is the original. We have x values. If you plug an x into the original, you get these values. But if you take the derivative, is the derivative less than 0 for these values? Do you agree, Dan, too?
Yeah.
Now how do you think it's 0, or why do you know it's less than 0?
Because f of x is decreasing.
Yes, f of x is decreasing. This goes down by 2. This goes down by negative 6. This goes down by 15. It's decreasing. So this is true because f of x is decreasing. Okay. Let's look at the second point. F of x, the original. So we're talking about the x values and the function values right here. F of x has a 0 between x equals 1 and x equals 3. So it's talking about these two x values here. And it's asking, true or false, is there a 0 between those values?
Yes.
See a lot of head nods. How do we know?
Because the fx goes from a positive to a negative, so it has to cross the x.
Okay, it's changing sign. It's going from positive to a negative. And the official thing that we actually learned about back in the notes is what's called, if you're asked a question about that, the intermediate value theorem. You know at this point you have a positive, at this point you have a negative, so there's some intermediate value that has to be a 0. So true because of the intermediate value theorem. Okay. Let's look at the third bullet point. The second derivative is greater than 0 on the interval negative 3 to 3. Let's take a minute and think about it. So the second derivative, greater than 0 on the interval negative 3 to 3. We know this is the original, We know that the derivative is less than 0. What about the second derivative? All right, Dan, do you have an answer?
That has to be false, as statement 1 is true, and you cannot have the double derivative be positive and the first derivative be negative. Because if the second derivative is positive, then that means that the first derivative is increasing, and if it's increasing, it has to be positive.
Okay, so another way to say that, which is correct, f of x is decreasing. F of x is decreasing at an increasing rate. Which means, so f of x is concave what? We said the second derivative, did we say this was true or false?
False.
We said it was false, so the second derivative is less than 0, so the original is concave down. So f double prime of x has to be less than 0. So then you can choose your correct answers. Which one has to be correct? A, B, C, D, or E? B. The second derivative is also less than 0.